Hi everyone, in this video we're going to look at modelling I guess a real life situation as a function and seeing how we might be able to answer some problems based upon that real life situation. So we've got the problem here of a biologist who was researching a newly discovered species of bacteria. Nice. At time t equals 0 hours, she puts 100 bacteria into what she has determined is a favourable growth medium. You know, it could be like an old smelly sock or something. 6 hours later, she measures 450 bacteria. Nice. Okay, so, and then there's a bunch of questions there, and we're just going to have a look at those questions one at a time. Now, in question 1, it says, assuming exponential growth, write an exponential model for the situation. So we're coming at this as an exponential modelling question. So I guess the first thing to do is to sort of highlight the parts of the question which we think are going to be critical. So let's have a look. Time t equals 0 hours, that's going to be important. The fact that she put in 100 bacteria to start with is going to be important. What else? It's a favourable growth medium. No, not so important. I guess the only important thing to note from that is that it is a growth medium. So we know we're going to have an exponential growth graph that's growing over time, not shrinking. 6 hours later, so every time I see a number I get suspicious that it's important. She measures 450 bacteria. Okay, so you can see what I've highlighted there. At the start, she's got 100 bacteria. 6 hours later, she measures 450 bacteria. So if it's exponential, I should be able to figure out what's going on there. So let's have a look at that in action then. So part 1 is to model that graph, model the function. So part 1. Oops, it's a bit thick there. Model the situation. Okay, well, what I can tell straight up from the situation is that there's nothing in that problem which seems to suggest that there's any kind of horizontal or vertical shift happening. So I reckon that we'd be pretty safe to determine that the model, let's call it, okay, we'll let P be the population of bacteria. That's pretty common to use P. And I like getting out of the habit of just using X's and Y's all the time. Let P be the population of bacteria. And T be the time lapsed, I suppose. The time that's moved on in hours. Okay, when you're modelling a problem, it's really important to do that setup. It's a good communication skill. So when I start putting symbols down, they have meaning to us. So at the moment, we don't know much about it. What do we know? We know that in general, I could say P is equal to K A to the power of X. That's supposed to be a K, believe it or not. There we go. Ka to the power of X. Okay, that's the general form of a population function where there's no vertical or horizontal shift, which we will assume there isn't any. It's not a bad assumption. Okay, so what can we do from here? Clearly we need to know what K is and we need to know what A is. Now believe it or not, it's not as hard as it looks, because the first thing to discover or to consider is, do we know what's happening at the start? And we do. At the start, there's 100 bacteria. That's really important because, sorry, I should just make that a T, shouldn't I? Just to be consistent. Silly me. Because when T equals 0, so when this value equals 0, then it doesn't matter what A is, all of this will be equal to 0. But let's just solve it as if it was an equation. At T equals 0, P, the population is 100. So what do we have? We have 100 is equal to K times A to the power of 0. Therefore, K equals 100, because whatever A is, raised to the power of 0 is 1. Yay, we've got that. i.e. P is equal to 100a to the power of t. So all we need to do is work out what a is, and we are golden. Okay, well, we also know that 6 hours later, she measures 450 bacteria. It says that there. 6 hours later, 450 bacteria. So 6 hours later is when t is equal to 6. 450 bacteria means that the population is 450. Awesome. So we can say at t equals 6, p equals 450. So we can use our newly minted value for k, 100, yeah, to progress ourselves a little bit. So we can say the population, the population, 450, is equal to k, which is 100, times a to the power of 6. So all we need to do is work out what a is from there. We can do that. We don't even need logarithms or anything. Let's just solve it. Divide this by 100, and therefore divide this by 100, and I get a to the power of 6. And I'll just write it as a decimal, I think. So 450 divided by 100 is 4.5. So what's a? Well, if I take the 6th root of a, I get a. Sorry, if I take the 6th root of a to the power of 6, I get a. So a is the 6th root of 4.5. That's the exact answer, but we might need to take an approximation for this. So I'm just going to bring up the calculator. I can't do this one in Spotlight, a 6th root. And I simply use this button here. Now on your calculator, you would type in 6 and then the root button and then the value, but this calculator works a little bit differently in that I go 4.5 and click on that and go 6, and I get that number there. Okay, 1.28. So a is equal to 1.28 to 2 decimal places. Okay, I might even go 1.285 and go to 3 decimal places. That gives me a little bit more confidence there. Okay, let's see how close I am. 1.285. Where's the power of button? There it is, to the power of 6 equals, yeah, 4.5. Okay, so that's pretty close, 4.50213, whereas where I'm expecting is 4.5 exactly. So it's pretty close. Not exact, so it's pretty close. So we can now conclude, therefore, the exponential model is P is equal to 100. I always use brackets rather than times. 100 bracket 1.285 to the power of t. 100 times 1.285 to the power of t. There we go. So that's part 1 done. That's probably the hardest bit, really, because you've got nothing and you've had to come up with some sort of formula. But once you've got the formula, you can use it. Part 2 is estimate the number of bacteria after 12 hours. Now, estimate might make you think, well, we just got to have a bit of a guess at it. But you don't really. I mean, it's an estimate because we've rounded a to 3 decimal places, and it's an estimate because in real life, you know, the bacteria is not going to perfectly follow the model. It's going to approximately follow the model. So that's why they say estimate, but that's what they mean. It really is a calculation from a mathematical perspective, and it says after 12 hours. That's critical as well. So let's go do that. So part 2. At t equals 12, so that's after 12 hours, the population is equal to 100 times, what was the number again? 1.285. 100 times 1.285 to the power of 12. And we just need to bring up the calculator again and chuck that in. 100 times 1.285 to the power of 12. Enter. There we go. So 2026.92. Okay, now That's 2026 bacteria, and 0.92 means one of the bacteria has probably had maybe a little bit of its blobby bits cut off, or maybe it's smaller than the rest. Okay, but that might be sizest. So maybe instead of saying that, we would say, well, let's probably round down. Often with populations, you probably want to round down. It's not a hard and fast rule, but because you are saying that at 12 hours, the population is 2026.92, we can say that it hasn't reached 2027. So in this case, we'd probably say just cut it off, round down. Therefore, the population after 12 hours is approximately 2026. If you said 2027, you know what? I don't think that anyone would probably be too stressed about you saying 2027 by simply rounding up. You know what I mean? So 2026, 2027 both of them would be fair answers in the context, I think. Oops, I had a calculator in the middle of that screen, but there it is there. 2026.92, the population after 12 hours is there. Okay, cool. So that's number 2 done. Number 3 is when would the population of bacteria exceed 500,000 bacteria? So we're looking for when it exceeds it. Now, my general philosophy is work out when the population would equal 500,000, and it's likely to be a fraction of an hour, and then you can say after that point it will exceed it. Okay, so let's just work it out, and I'll show you what I mean. So 500,000 bacteria. So this is number 3. This is a population this time, isn't it? So the population is 500,000, and we don't know the time. So we start off by filling in the bits we do know. 500,000 is equal to 100 times 1.285 to the power of t. And then we basically need to get t by itself, and we can use a bit of logarithms for this. So if I first divide both sides by 100, I get 5,000, I hope, yep, equals 1.285t. And then we're going to use our logarithm knowledge. So we know from our logarithm definition that if a to the power of b equals c, then log base a c equals b. Okay, so I just put those there in red so we can match them up, right? So there's a. So I will go log base 1.285. Unusual base, but nevertheless it can be done. And then log base AC, so there's C, 5,000. Log 1.285 of 5,000 is equal to T. Now I might switch these sides around because having T on the right-hand side, there's nothing wrong with it. It's an equation, so it doesn't matter where T is, but I don't know. I just feel a little bit like, because I guess from, my background, I read from left to right. I feel like as if the thing I want to find out needs to be on the left. It's just it's just one of those things that's unnecessary, but to me makes more sense if we do it. So I'm going to flip those sides around, but I'm also going to apply to this log base, I'm going to apply change of base as well. So T is equal to, I'm going to use log base 10 because my calculator does base 10, log of 5,000 over log of 1.285. Okay, now that's using log base AB is equal to log B over log A. So that's change of base. Okay, that's good news for us though, because we can use our calculator for that calculation there. So I'll draw up the calculator again. Oops, not the calculator, that's a very different thing. So we've got log of 5,000, so I go, on my calculator I have to put the number in first, so 5,000 log. divided by 1.285 log equals 33.965. I'll just get that down, then I'll get rid of the calculator. 33.966 to be precise. Okay, so that's what t is equal to. So the population is 500,000 at 33.966. But we'd probably want to use the nearest hour. So at 33 hours, the population won't be 500,000. So we're going to have to round up to 34 hours. So I would conclude, therefore, after 34 years, oops, not years, that would be a very slow population growth. Try that again. After 34 hours, the population will have exceeded 500,000. Okay, so that is basically question 3 done. Last one is question 4. Question 4 says sketch a graph of the model. So what we're going to do now is do a quick sketch, and that will finish this off. We've got all the information that we need, and the sketch won't take long at all. I simply, so this is number 4, sketch. Couple of things in real life situation, make sure that when you draw, I'm going to have to just not use a ruler, but you know, do as I say, don't do as I do. Make sure you label your axes properly. This is population versus time. Now, because this is a real life graph, real life situation, you have to realize that you don't have to graph down here. So you know the normal exponential graph sort of goes like that, but you don't need to do that this side of things, because the population will never be, time will never be below 0. You know, unless you're a Time Lord and you have a TARDIS and you go back. But assuming that you can't do that, there's no point in going past that. So what you do is you simply mark off what you think is fair enough for 100, and it's exponential. So you simply do a sort of a swing up like that. And that's basically it for a sketch. If I asked you to graph it instead, then you might need to use 500,000 down here somewhere, and then sort of put a point up here, which would be, 34 down here, and put a mark up for 500,000 up here to give you a bit better, more of an idea of the sketch there. But this is basically it for the sketch. Simple as that. Okay, so in summary, let's just quickly look at that. The order of questions here is pretty standard for this kind of problem. Number 1, model the problem. Number 2, see if you can work out what the population would be after a certain number of hours, or whatever the growth variable, the independent variable, is telling you to do. Number 3, what would the population be? What would the time be given a population? And number 4, maybe a sketch. So there's number 1, modelling it. Number 2, there's calculating a population. Number 3, there's calculating a time given a population. And number 4, there's a really rough sketch of the problem. And that's it for me. Thanks very much, everyone.